Okay. So they always put me right before lunch or right before beers in the hope that they'll probably wake everyone up. So yeah, my name is Francesco. I've been doing Erlang since 1994, initially at the Computer Science Laboratory, Ericsson, and then later with Erlang Solutions. And this story, or what I'm going to talk about today, is not about the book, but about the whole process of writing the last 4 chapters of this book. So, how many of you have written a book here? A few of you have, yes. So, you'll know that if you go in and write a book, as soon as you're holding the paper copy, it's a bit like having children. You forget all of the hard work, you forget all of the pain, and next thing you want to do is go off and write another one. And so I wrote the first book, Erlang Programming, in 2009. It came out in 2009, and immediately we wanted to go off and write the book, the follow-up book, the book on OTP. And that project luckily got delayed until 2012, when we finally kicked off and started writing this book. And when I usually write books, what I do is I take the training material here at Erlang Solutions, which I developed. I start use those examples. It's taken quite a few years to develop them. They've been tested, battle-proven, and I start lecturing. And I continue lecturing. And when I'm done, I go back. I think of where did the students struggle the most, and I make sure that text is really clear. And then I start thinking, what did all of the smart students, what hard questions did they ask? And those end up becoming sidebars or side notes. And then, that's it. And then I throw it over to my co-author, who usually goes in and removes all of the corny jokes. And it goes backwards and forwards a few times. And that's exactly what happened with designing for scalability. So, we went in and described OTP, all the behaviors, design principles. And chapters 2 through 12 went relatively fast. It took maybe a year and a half to do. Now, I then finally reached chapter 13. 13, especially in the States, it's never a good number. And in chapter 13, what I was trying to do is, there seems to be this popular belief that by magic, just because you're using Erlang, your system will never fail, and it's going to scale linearly to infinity. And, well, those of you who've actually been doing it know that is a myth. That's not really the case. And I wanted to go in and bust the myth. Go in and explain that there is some truth in it. The truth is that there is no magic behind it, and that indeed all of the concurrency, all of the error handling, all of the semantics we've got in Erlang make it much easier. But they don't necessarily, solve. They'll remove a lot of the accidental difficulties you'll come across. But intrinsically, it's still a very hard problem to solve. And so, the architecture was, this chapter was supposed to be one chapter on how do you go in and start architecting your node and how do you connect nodes together. And I start writing. Then I write a bit more, and I continue writing. And I was actually looking it up a couple of months ago, and I found a letter which I was sent to my editor. Oh, in a few weeks I'll be done with the chapter, I'll be sending it in. That was March of last year. So I've got at least maybe 1 or 2 weeks left. That was March of last year. In November, I was finally done with chapter 13. And what happened was, writing, putting down ideas on how to do things, ended up turning into 80 pages. And there was no training material. It was all, I was just doing a big brain dump over everything I do when I go in and start architecting a distributed system. And, and these 80 pages basically resulted in all the steps involved in designing and architecting a distributed system, and documenting all the patterns you need to deal with along the way, and then pointing out everything you need to think about when it comes to resilience, when it comes to reliability, when it comes to availability, and so on. And that's when we realized actually that this chapter was in fact 4 chapters. The editor, no, this is way too much, and we knew it, but I was stuck. We were, Steve was stuck as well. We were just, break it up into 4 chapters. And this is what we ended up breaking it up into, So first of all, how do we go in and deal with distributed architectures, systems which never stop. So how do we make sure that your system is available even when, will respond to your response even when things around it are failing. And finally, scaling out. And having gone in and broken it into these 4 chapters, that's where, things slowly started falling in place. And it's these 4 chapters, I'm going to focus on in this talk. Now, and so starting with chapter 15, the first, chapter 2 to chapter 12, all cover, how you start with a process and making that your basic building block. You give it a behavior. You put processes to get into supervision trees, package them into applications, and put your applications together in your standalone node. Yep, that's fairly straightforward. And OTP has always done a great job at telling us how to architect everything on a single node. What we started looking at that point was distributed architectures. How do we start combining together distributed these nodes, and how do we make them interact with each other? And we quickly came to realize that right there, OTP does a great job at providing a common terminology, but it stops at one single node. And in the process of writing this book, we were also working with the release project, where we created something called DECO, the Distributed Erlang Component Ontology. And it's a paper which you can find online, where we try to describe names and give names to components in distributed architectures. And I'm just going to cover some of them here, but everyone we discovered was using different terms. So some people were calling, think of a 3-tier distributed architecture. We'd have front-end nodes. So that's maybe where you would be running your web servers, which handle all of your REST requests or HTTP requests. They convert everything into Erlang terms and pass them on to backend nodes, also, which we refer to here as logical nodes. And they maybe go in and hit some other nodes, possibly even written in Erlang or some other language, which could run a database. And so we started defining this architecture and how these nodes are grouped together, giving them specific names, which would then become, and that's the terminology we start using in the remaining chapters. So the important ones here to think of are front-end nodes. So these are nodes which are usually client-facing. You've got logic nodes. These are the nodes which contain your business logic. And finally, you've got service nodes. These are nodes which will provide some form of service. It could be a service towards an external API. It could be a database. It could be a cache. It could be a payment system. And so once we described this, we went ahead and started providing a set of steps, which I walk through when defining an architecture. And the first step was go in and start dividing your functionality into node types. So what you want to try to figure out is what responsibilities do you want to give individual nodes, and see it as microservices, see it as self-contained functionality, which allows you to go in and optimize these nodes based on the particular hardware deployment. So you could have front-end nodes which become very memory intensive because you need to keep a lot of TCP/IP connections open. You could have service nodes where it becomes very I/O intensive, where you're storing a lot of data on disk, for example. And so by breaking it up into smaller services, almost standalone services, you're then able, you give each node a specific responsibility, and you're then able to start optimizing the hardware and all of your deployment strategies, your network connectivity, and so on. So first step, with any distributed architectures, divide the functionality into node types. And what we then do is we start grouping these node types together to create what we call node families. So node families are nodes of the same type within the same cluster. And then once you have a cluster, you can start deploying multiple clusters. Yeah. You're following me here, so? Yeah? Great. So once you've divided the node into node family, the next step you need to take is describe what distributed architectural pattern you're going to use. in probably 90% of all Erlang, of all cases when we're dealing with Erlang or even Elixir for that matter, the most common and most basic architectural pattern is the fully meshed one. So you've got your Erlang nodes and they're all connected to each other. I mean, a fully meshed architecture can handle, I think, most loads of probably a good majority of the systems out there. Now, it does have its problems, obviously, as your scalability is limited to maybe 70 to 100 nodes. Work's being done to increase that. We heard that from Kenneth yesterday, but you still have certain limitations. So if you're not sure that, you usually start with that. You start getting something out and running. So that's one of the patterns. Another very common pattern which we're seeing out there, and it's thanks to React Core, is the dynamo principle. So this is the slide you've probably seen at every single Basho presentation. And if you are at the Basho presentation and you don't see the slide, you can be sure that the presenter is not being paid or doesn't work for Basho. In this particular case, I actually borrowed from the Basho is not paying me. But what you do with the whole dynamo principle is that you go in and you think of a key space. So you've got a key space, and with your key space, you break it up into 2 to the power of 160 potential keys, and you assign each a certain number of spaces, a certain number of keys to a particular partition. And then you divide these partitions across multiple nodes. So in this case, we've divided the partition into what was it now? Into 16 nodes, sorry, into 16 nodes. And what you do is you have your particular session key, so you have a unique identifier, a unique key. And what you do is you hash on that key, and it gives you what we call the V node. So it's one of these little partitions, and once you know the V node, you'll get the routing to your physical node on which that session or that particular data is stored. And what you then do is on every physical node, you have a certain number of partitions. You have a certain number of V nodes. And by using your consistent hashing and virtual nodes, you can then take a step forward and start replicating the data. So, this physical node, Erlang node 1, will contain V node 1 and V node 5. You could theoretically go in and replicate V node 1 here and V node 5 here. And using this replication, what this gives you is that if you lose a node, the requests get routed to your backup node without having to rehash all of the nodes which are still up. So you just end up rehashing these nodes, but you do that balancing and consistently across your existing nodes. And using this approach, you basically use your React Core as a way to distribute your data, as a way to get your fault tolerance, and also to go in and allocate your jobs, do the job allocations. And we're in San Francisco, but just a few weeks ago, Goldman Sachs went in and described their whole job scheduling within Goldman's and how it works. And they schedule about 1 to 2 million tasks a day, each task running between 3 seconds to a few minutes. And they're doing it using React Core and using exactly this architecture, where all of your kind of React Core nodes are there and act as some form of a giant switch. They receive the requests and they will forward them to the right nodes. And then what you do is you hook the different, your different React Core nodes, which run all your business logic, to front-end nodes. So you receive your front-end requests, which then forwards them on to your logic nodes. And forwarding them to the logic nodes, they then get executed and then moved on to the service node. So you need a certain task, you pass it on to the service node. You need to store it persistently, you pass it to a key value store maybe somewhere else. And using these types of architectures, you basically start having no single points of failure, and your actual core here will increase to about, you can increase this to about 70, 80 nodes. Guess is, you could probably run Twitter on 10, 20 of these nodes, all of the Twitter traffic on 10, 20 of these nodes. Goldman Sachs actually had 7 nodes. They ran all of their traffic on 7 nodes. On a React Core with 7 nodes. And it's a question of routing messages, job specification, replication of the session state. And by creating then these islands, that's where you start getting all of your heavy scalability. So I think, with Twitter, the biggest issues are not the routing of the messages, it's the search functionality, it's serving the timelines. And you start doing these in these islands all around your React core cluster. Now, this is another star topology. This is another typical, almost linearly scalable architecture. And I've seen systems with the star topology expanding to millions of requests per second. All you do is you start adding more service nodes to the tails and contracting them when you don't need them. Another very common architecture is the service bus architecture, considered a bit enterprisey by some. So if you think that service buses are enterprises, just think in terms of microservices, which is pretty much the same idea. You use a service bus, and to it you can then connect your front-end nodes, you can connect your logical nodes, and your front-end nodes and your service nodes. And so as you're building your distributed architecture, you need to start taking into consideration now scalability and also reliability. And these are things I'm going to get back to in a second. But these are things, start thinking, how do we ensure that there's no single point of failure with this particular architecture? How do we make sure that it's not, where are the bottlenecks and how do we scale? Another really interesting distributed architectural pattern, which I've actually never seen in production in an Erlang system, we've played around with the ideas, but we've never done it, is peer-to-peer. I mean, this will be the most scalable distributed system of them all. Think of BitTorrent, think of Kazaa, where all of the logic nodes act both as a server and as a client. So they're all identical and they all connect to each other. And using this principle, we can then go in and start creating our islands right here with front-end nodes, with service nodes, expanding the system as and when it's needed. And once again, this is connections coming up and coming down. And if any of you have ideas over potential architectures, using peer-to-peer, come speak to me. I'd love to get some concrete examples of it. So these are, I think, the most common distributed architectures to think of. And once you've put them in place, the next thing to think about is, what network protocols, do you want your nodes, to talk in between each other with? Your node families which you're connecting. What network protocols do you want your node families to use when communicating? And note so far, I've only mentioned distributed Erlang, but distributed Erlang is not always the right approach. We've seen, systems with MPI, 0MQ, UDP, SSL. In some cases, they'll go as far as using REST, AMQP, SNMP, XMPP, MQTT. So there's a large variety of protocols you can choose, and you can pick anything as long as it's not Corba. You're fine. In this particular case, I mean, this is your typical front-end web servers, which are customer-facing. So all of these nodes are facing the internet. They're facing public, insecure networks. And what you tend to do is put firewalls. If you're still using physical machines, you will have separate networks facing which the clients are allowed to communicate, and then a separate network internally. So you're actually physically separating the front-end nodes from the logical nodes. If you're running in a cloud environment, you'll do the separations logically as well. But in this particular case, it wouldn't be too smart having a firewall and then having distributed Erlang running between the front-end node and the back-end nodes. Anyone gaining access to your front-end nodes, even if they're stateless, would then, using distributed Erlang, be able to do whatever they wanted with the back-end nodes. So what we tend to do here is just use, for example, SSL, and then be very careful over what functionality we allow to go in between the front end and the back end nodes. So once you've got in and you've defined what network protocols you're going to use to connect your nodes and your node families and your clusters together, and mind you, it could be a mixture of many. So you could use distributed Erlang within your cluster, and then maybe TCP/IP across clusters, as an example. Once you've done that, the next step you need to think of is defining your interfaces, and beginning to make design decisions over, what state and data models, over your state and data model. What data do you need in what nodes, and what will the interfaces in between these different nodes look like? So, you might be working from a proof of concept. You might be working based on stories, so you might have user stories. So, there are many different ways of starting to pin down these particular, these particular interfaces. But it's really important you start doing it at a very early stage, and that's probably the fourth stage, the fourth step you'll look at, and understanding, once you've done your interfaces, go back and look, what data do you actually need to start duplicating across what nodes and how. And what this gives us basically is, what this step does is it will go in and validate your choice you did in step one with your node functionality. What functionality you want to put in the individual nodes. You might realize that you've put functionality in this node, which maybe requires data which is in this node. And so it might not always make sense, to do a remote call every single time you're going from one node to another. You want to reduce data redundancy. That's another thing. You don't want to duplicate data across multiple nodes if you don't have to. And once you've validated your design choices in one way, you pick the node types, the next thing you need to do is start thinking of standardizing your APIs, making sure that all your APIs are very similar from one node to another. And at that point, what you'll have is you'll have your different nodes, connectivity between the nodes, interfaces, and an interface which you can start developing. And that's more or less the point where you need to start thinking of failure. So you need to start thinking of availability. Availability basically defining the uptime of your system over a certain period of time. And what we tend to talk about is availability being the result of your system having no single points of failure, which I'm going to get into in a second. They have to be fault tolerant, resilient, and reliable. So starting with fault tolerance, fault tolerance is the ability of a system to act predictably even under failure. So in this particular example, the client is going in and sending a request to the front-end node. The front-end node passes it on to a logic node, and something goes wrong in the logic node. It could be the network connectivity towards the logic node goes down. It could be a process crashing in the logic node. It could be the node itself, the Erlang node crashing. It could be the hardware crashing. Or it could be a very busy node. A non-responsive node is equivalent to a dead node. And we don't know if this node is incredibly busy. So what happens is we either return an error or a timeout. But what is important is that we do return something back to the client saying, I was not able to service your request, or I'm not sure if I was able to service your request, maybe, maybe not. But sending back a response, sending back not a response, basically makes the system non-fault tolerant. So something worked or something didn't work, we don't know. That's acceptable. And you then start dealing with that issue in the client itself. Your next thing you need to start thinking about is resilience. And resilience is basically the ability of a system to recover from fail. So you go in from failure. So you go into your client, you send your request, and say the front end crashes. It restarts quickly, or another front end kicks in and starts taking over the request. So when the client resends the request, the request gets passed on to a logical node, and we get a response back. So, that's another problem. You need to start thinking, what you tend to do is, we say let it crash. What you tend to do in these cases is actually put your effort into the recovery of your system. And you need to make sure that when your system restarts, your restart actually gives you a consistent state. So that if it's corrupt data or a corrupt state, that you've actually addressed and resolved the problem when restarting and recreating your state from scratch. Now, the third thing to start thinking about here is reliability. So reliability of a system is the ability of a system to function under particular predefined conditions. And these particular predefined conditions could include, and will include, especially if you're working with distributed systems, errors or inconsistent data. So assume we're actually going in and sending a request, which gets forwarded to a front-end node, This request then gets handled by a logical node, which crashes or times out. The front-end node receives that request and gets told that, look, there's an issue happening, and forwards it on to another logic node. This logic node then handles that reply, handles the request, sends back a reply, and the client has no idea that something's gone wrong behind the scenes. Yeah, that's the reliability of a system. So even though something's gone wrong, we still have serviced that particular request. And so, looking at reliability, when you've started thinking of resilience, reliability, and fault tolerance, that's where, for every interface you've implemented in your function, you need to start thinking about a retry strategy. So if you think here, just look here. We send a request to the backend node. Do we know if the backend node here has successfully executed that request? We're not sure, and we don't know. It could be that it's an incredibly busy node. We get a timeout. We execute it on another node which is not as busy. So it might happen that we maybe execute that request twice. It might be that this request here is never executed because the node crashed before it was able to do so, and so this is executed once. So for every interface function in all your nodes, you need to start picking a retry strategy. And by retry strategy, we mean that do you want your request to be executed at the most once? At the most once means you execute the request and then you fire and you forget about it. So, do you want it to be executed at least once? So you want to make sure that you've executed it, but if you're not sure if it's been successful, you continue until you get a positive acknowledgement. Or there's a third one, which is exactly once. Do you want your request to be executed exactly once? And exactly once is the trickiest one, and I'm going to get into it in a second. But exactly once, as long as you've got a network, you cannot guarantee that you've executed something exactly once, because you might have executed it, but then you start getting network issues before the acknowledgement comes back. So what you know is that either you've executed it successfully, or you've left your system in an inconsistent state. And I'll get back to that particular thing. So for every interface function in your nodes, you need to pick a retry strategy. So exactly once, at the most once, or only once. Once you've done that, you need to start thinking about your data sharing strategy. What you tend to do with your data is you distribute your data for scale, and you replicate for availability. So this is the strategy you need to keep in mind. And so another very typical pattern we get is, assume we've got an e-commerce service where you need to be logged on in order to buy things. What we're doing here is we're showing the share nothing strategy. With a share nothing strategy, a client will go in, it will set, will log in, the login request gets sent to a login node, and the session gets stored in that particular logic node right here. Another client goes in, it gets routed somewhere else, and that session gets stored elsewhere. But these two sessions are not shared. So basically, the share nothing strategy. Now, if a fault happens right here, and we send in a request, the logic node fails, we forward the request onto another node, assuming it's client 1, the node which receives it only is storing session 2, it returns back an error, unknown session, forcing the client to log on again and then recreate a new session on this other node. So this is the share nothing approach. So what you do is you handle failure often up on a client level. So usually by going in and creating another login request. Another approach with data is share something. So assume we go in and we only share sessions across at least one computer. So we go in, we create a session, which gets stored on both logic nodes, on both backend nodes, and we then decide to buy a book. What we don't share across nodes, though, is the shopping cart. So we buy a book here, then the node terminates, and when we go in and buy a train set, it gets stored on this node. And at that point, we only have, we've lost the book. This node might come up again. We might reread the book from a persistent storage. we might try to merge the two nodes together later on. That's usually done in libraries, with eventually consistent algorithms. But this is the the share something approach. So that's the second thing you need to think about. Then the third approach is the share everything approach. And with the share everything approach, what we have here is an example of primary replication where we copy everything. We go in, we have a session which is copied, we buy a book, it gets copied on all nodes. We go in, we lose a node, we buy something else, you buy a train set, it gets added here, and then when this node comes back up, we copy over the data, and we decide to remove a book, and it gets removed on both nodes. So obviously, this becomes your most resilient system, but also the most expensive one to run. And this here is an example of primary replication in contrast with primary secondary replication, where in primary secondary replication you can read and write on one node, but you can only access the data on the second node. And one of the things we need to start dealing with when we're looking at share everything architectures are network partitions. And there are many things. What happens if we get a partition network? We get a book on one side, a train set on the other, and then the network comes back up again. We need to go in and start merging these items. And depending on the tools and the algorithms you use, you could use eventual consistency, described in the Dynamo paper. You can use CRDTs. There are many approaches here on doing it. And I think go to one of these talks if you want to dive more into them. But once again, these are one of the things you need to worry about. And finally, there's something called idempotence. So retry strategies. What happens if you're doing, say, for example, a payment? Now, when you're doing a payment, you want to make sure that this payment happens only once. So what happens if we go in, we want to do a payment, we send back a reply, the payment's successful, but the request fails. The response fails back and we get a timeout. We go in and we send the request again. It's now up to the business logic of your system to ensure that that payment goes through only once. And and there are various ways of dealing with it, but often you notice that it's a duplicate payment. You send back a duplicate reply. The client gets back saying, "Yep, your payment went through, not a problem." And this is once again a fairly expensive approach, but it's an approach you need to do when you need to guarantee the consistency of your data. And that's where something called idempotence comes in, which is the ability for the same function to be called multiple times, but changing the state only once. So if you're dealing with payments, for example, it's usually a two-step commit, where you go in and you first reserve the funds, and you get back a unique identifier. Once you have that unique identifier, you use it to commit that payment. If you lose that unique identifier, you don't commit that payment within a few hours or a day, then the reserves you fund get freed. An even simpler example is cashing in a check. You've got a check, and you've got a unique identifier. You can only cash in that check once. And you try to cash it in again, it will fail because it's, once again, the transaction's already been made. So when you've looked at all of your, the consistency and the availability and your recovery strategy and your data sharing strategy, you might not realize it, but you've started making trade-offs. And these are trade-offs which will start appearing in your system. And looking at availability, so nirvana would be, to reach this little point here in the graph. We want systems which are really strongly consistent and highly available. That's really, that's the ideal scenario. Truth is, if we go for the exactly once approach, this is obviously the most consistent approach. We know that the data is going to be identical across nodes, but it's also the least available. If you need consistent data across two nodes, you might be forced to take your whole system offline to guarantee that consistency. As soon as you get a network partition, you need to take your system offline, or make sure you've got a hot standby which gets shut down immediately. With the at least once, it starts becoming, you start getting, your data is not as consistent, but it becomes much more available. And obviously, the most available is the most ones, the whole fire and forget approach. Fire and forget is typical when you're, for example, dealing with non-premium SMSs. You send SMS and just hope that nothing fails there in between. And if it does fail, well, the system sends a few million SMSs per day. You'll lose a few. You won't get blamed for it. Instant messaging is the same. You still go for the most ones. Payments. That's the exactly once approach. And so this is, these are the trade-offs you've done with your recovery strategy. But if you're looking at the sharing data, once again, the most available system is the share everything. So, sorry, the most reliable is the share everything. You've got data copied. The more copies of the data you have, the more reliable your system has. But that comes at a cost. It's very expensive to actually copy all the data across nodes. And B, it's even more expensive to keep it consistent. And that's what hits into the availability. So if you need strong consistency, it won't be available. And just like the exactly one strategy, you might have you take your system offline to guarantee the strong consistency. The share something is not as reliable. So if we're only sharing, for example, the session, but not the data, we might not have to log on again, but we might lose a book. So your reliability is lowered, but your availability goes up. And finally, the share nothing is the most available. You're not sharing any data. You're in effect sharding. You lose a few nodes, you're fine. But you're losing the data associated with those nodes. And so, so those are the next two steps. So for every interface function, you need to pick your retry strategy. And for all of your data, you need to pick your sharing strategy across the nodes and node families. And when working 5 and 6, you will most probably go back and also start reviewing all the strategies in 1 to 4. What is the functionality of the nodes, your architectural patterns, and your sharing of data. So once you've decided about your fault tolerance, that's when your whole scalability comes into the picture. And the fact is that when you're scaling out, you have to carefully go in and integrate all of this with the consistency and availability models. And in fact, the design decisions you already made will now go in and impact how your system scales. Back in the good old days, you used to have centralized servers, and to scale, you scaled vertically. You got a nice, bigger, faster, shinier computer, and you waited 1.5 years, your program would run twice as fast. Now, unfortunately, this approach is very limited. Servers can only get so big, and the bigger they get, the more they cost. And try to picture an OSI model, the OSI model. The OSI model tells you how to now go in and scale vertically, if you think of it. And what we're trying to picture here instead is an OSI model which tells you how to scale horizontally. And your horizontal scalability is just solving your scalability issues by throwing hardware, a bit of commodity servers at the problem, or a few more instances on Amazon. And the problem all of a sudden you start getting there with scaling horizontally is that you need to start distributing your data, and you need to start distributing with, dealing with your network. And these are already, design decisions you've taken. And that's why I'm saying you might have to go back and revisit your distributed architectures, because if we look at the whole sharing of data right here, sorry, if we start looking at at your scalability, so this is actually our trade-offs in scalability, the exactly once approach is the least scalable of them all. So it's not going to scale at all, because you need to guarantee a response, and as soon as you lose network connectivity or something abnormal happens, you need to stop. At least once, you keep on trying until you get back a response. So that's it's least consistent, but it becomes much more scalable. And at the most ones, that's your most scalable one. You don't need to store any state. You send off a request, and you don't need to wait for a response. You don't care about the response. You just assume that it's executed. And if you've lost it, well, it doesn't really matter. And that's how your recovery strategy affects your scalability. Sharing data does the same. Share everything. It takes a lot of networking resources, CPU and I/O, to share the data, and so it becomes your least scalable. Obviously, it's still your most highly available. Share nothing. Scalability is a bit better. Share nothing. Share something. It's a bit better. Share nothing your architecture, well, becomes almost linearly scalable. It's in effect sharding. But then again, it also hits your availability, because if you start losing data, depending on the semantics of your program, you start having problems. Having come this far, the next thing you need to start looking at is capacity planning in your system. And usually the only way to load test an Erlang system is using Erlang itself. The same applies to Elixir. So you load test Beam using Beam. And what you'll find is usually the hardest part in capacity planning is generating enough load actually to saturate your system. I mean, Francois this morning was talking about chat rooms with 3 million, 4 million users. You can't really go out and ask 3, 4 million users to start playing a game at the same time and say, nope, failed, crashed, bang. You actually need to start simulating intelligent usage of your system. And you do that using load tools. Often you need to write your own. And what you do with the capacity planning is you start pushing optimizations to things which are outside of your control. So you start loading your system and start pushing all of the performance issues to external services. More often than not, you'll have to write also your own simulators. And that will tell you, the three things you're looking for is, first of all, breaking point. What is the breaking point of your system? What load can you actually manage? How many simultaneous users per second can you handle? How many messages per second? Things, and you're using these things to then understand how your system will behave under extreme heavy load. And with this data, you then use it for load regulation and back pressure. So, back pressure is the ability to reject calls. So assume your system, that your system will break after 1 million users. What you do is you start rejecting requests, if you have 1 million users simultaneously logged on. And the second thing you need to think about is load regulations. And load regulation is usually done through queuing. And what you do is you start pushing out, when you've pushed out your performance bottlenecks, your third parties, what you need to do is make sure you don't start syncing your third-party APIs. And we've had, we were load testing some of our voice over IP systems, and we were testing them against simulators at one point, not realize, we thought we were testing them against simulators, let's put it that way. And in fact, we were actually connected towards a VoIP provider. And this was 3 days before going live, and managed to sync that whole VoIP provider's infrastructure, causing them probably a 3 to 4 hour outage. They were not too happy. They kicked us out. We were not too happy because we had to then integrate 3 days before going live with another VoIP provider. But that's where you start. Don't go in and learn that your third-party APIs don't have any back pressure. Go in and actually start putting load regulation here itself. And what you do is you use queuing and load regulation, which will basically handle your peaks and troughs. So if your third-party API has a service level agreement of 300 requests per second, make sure that you allow a maximum of 300 requests per second to go through. And what you then do is, if you start getting an overflow here, so if the third-party API can't handle enough requests, at this point you start rejecting calls, or requests, which with errors being sent back to the clients, asking them to retry later. And then that's capacity planning. And at this point, once you've got your capacity planning, you need to start developing what we call a cluster blueprint. And a cluster blueprint is used for scalability. It will describe how many front-end nodes do you need for every back-end node and for every service node. And so when you start scaling up and adding more capacity, you know that if your front end handles 1,000 requests per second and your back end node 2,000 requests per second, you know that for every 2 front end nodes, you need a back end node. And and at that point, if you've proven that you've got no single point of failure, that means if you can lose any node, have issues, lose network connectivity to other parts. Once you've proven that all of this works, go in and you've got your cluster blueprint. You've done your load regulation, you've put in your back pressure, throttling requests. You could actually use for load regulation and back pressure, There are two really good libraries out there, Jobs by Ulfiger and Safety Valve by Jesper Louis Anderson. They're the ones we tend to use. Once you've done that, the next step is looking at monitoring and preemptive support. And this is another different story. I'm not going to get into it now, but what you need to make sure is you need to have full visibility in your system. You need to be able to detect that some issues might escalate. If you want 5 nines availability, you need to address issues before they happen. And that means getting early warnings of these issues. And that's where monitoring and preemptive support come in. So this is basically what happened. This is what I ended up describing. And it ended up taking 6 months. It sounds simple now. You make architecting these systems appear simple, but putting in all the thoughts, and the whole thought process which goes through from starting from a single node to actually document all of these patterns ended up taking the time it takes. And the 10 steps, the 10 easy steps towards architecting your Erlang system now include splitting up your system functionality into your standalone nodes. If you're buzzword compliant, you're very welcome to call them microservices. Decide what distributed architecture you're going to use. So start thinking in terms of distributed architectural patterns. Do you want to go React Core? Do you want to start using clusters, peer-to-peer? And decide what network protocols you want your nodes, your node families, and your clusters to use. Define the node interfaces. That's incredibly important because your node interfaces become your entry point to these nodes. That's usually what you're going to test. That's usually what you're going to load test. And define your data, your state and data models across these nodes, trying to reduce the need to duplicate data and whilst keeping fault tolerance and scalability in mind. Once you've done with all your APIs, pick your restress strategy. So exactly once, only once. So exactly once, at least once, and at the most once. And when you've done that, pick your data sharing strategies across families, node families, clusters, and types. Reiterate through all of the previous steps until you've actually managed to get all of the trade-offs you need. Because picking your distributed architectural patterns, you will have made trade-offs between reliability and scalability. And you need to go in and find the right balance. Design your cluster blueprint, which will look at all your ratios you need for scaling both up, but scaling down as well. And identify where to apply back pressure and load regulation for your capacity planning. Learn how your system works under pressure before you go live, not once you've gone live at 3 o'clock in the morning when America's waking up and everyone starts using your system, at least for those living in Europe. And finally, define your operation and maintenance approach. What you want to do is define all your system business alarms and metrics and make sure you've got full visibility. And the last piece of advice is don't go in and over-engineer your systems. I know you all want to implement, become the next machine zone or the next WhatsApp, but it's not important to get something which works fast or is highly scalable. You need something which works. And once you've got something which works, bring it to the next level. And if you start thinking with these things in mind, you start having concise APIs and data sharing strategies, you don't need something massive. As long as you've architected it right, something small which will work end-to-end can easily then be scaled and give you the resilience and the fault tolerance. You've got a lot of the semantics in Erlang and Erlang Virtual Machine, out of the box, which gives it to you. So, advice: don't over-engineer it. Don't start thinking about 20 million user chat rooms with 3 million users. Start thinking in terms of chat rooms which will work and handle everything, and then from there, take it over to the next step. Yeah. And that was it. This is the book. We've actually started production now. So for those of you who have been waiting for a copy, hopefully you'll have the Dead Tree one in about a month's time. For those of you who don't, I'm sure you can find it on BitTorrent if you like to try before you buy. Any questions or any thoughts? Yes.
The process is very complicated, right? And decision you make, you have just to guess which decision have what price. Do you have some kind of modeling system when you can play with that without?
It's every Erlang project should always start with a proof of concept. If you want to fail, you want to fail on a small scale. And so yeah, that's how I would do the modeling. And what you need to address in your proof of concept is always your concerns you might have. So if you've got concerns on scalability, your POC needs to show that your system can scale linearly. If you've got concerns about reliability, you need to be able to prove that it's reliable. So, pull out network cables, break machines or whatnot. Yeah, if you break the machines, yes, very, yes. But, yes, so, yes. So that's really, there are no models I'm aware of. And not only, and the reason I wouldn't go down the model route, but actually a proof of concept, is that you get so much, your data, every system behaves differently. So what might be a bottleneck in one system might not be an issue in another. So it's very hard to model. Yeah. Carl, yeah.
Yeah. So, yeah, in the Internet of Things, although we might be wisely running Erlang, it's highly likely that they are not. Nevertheless, we have to figure out how to interface with them and play nice with them, or we will survive.
Yes. So true. Yep. And that's where you're looking at interfaces and looking at network connectivity. You need to start. Yeah, that's where that mindset comes in. Assuming that connections go down, if you're
At any point you lose any device, including us.
Yes, exactly, and.
So we have to figure out how to push the stuff that we have that's precious over to them, so that we're the next one to go. The information survives.
That's right. That's correct. And I think that's where, as I'm seeing it, network protocols and interfaces come into the picture. So it's not just an Erlang API, which I refer to here, but it could be any standardized protocol, and obviously your connections could be secure as well, as we're seeing these days. Okay. I'll be around. Feel free to reach out if you've got any questions. Thank you very much.